Hi, my name is Steve Matsumoto, and today I'll be presenting CAPS, a system that aims to provide a smooth deployment roadmap for security improvements to the Web PKI. This is joint work with Jay Basamiya, Yucheng Dai, Paul Van Oorschot, and Brian Parno. The overarching goal of this project is to prevent man-in-the-middle attacks in the Web PKI. In a standard TLS handshake, Alice and Bob establish a shared secret key using Bob's certificate, signed by a certificate authority or CA. They can then use this key for encrypted communication between them. An attacker Eve on the path between them can replace Bob's certificate with their own, and as long as Alice trusts Eve's CA, she'll establish a shared key with Eve without realizing it. Then Eve can read and modify messages between them without either of them knowing, thus successfully carrying out a man-in-the-middle attack. Now, our paper describes a wide range of approaches to mitigating man-in-the-middle attacks in the literature, but here are two that motivate the major goals of our work. Certificate transparency, or CT, requires CAs to publicly log every certificate they issue before they can be used. This makes it easy to detect certificates that might be used in a man-in-the-middle attack, and in part because CT is developed by Google and well integrated into Chrome, it is widely deployed in today's web. Additionally, since CAs typically send their certificates to the log, the PKI and certificate issuance process look largely the same as it did before. The system does have its drawbacks. CT doesn't actually prevent man-in-the-middle attacks, and there's no way for a domain to signal what its true public key is. ARP-key addresses these two problems by using multiple trusted parties working in conjunction to issue certificates. Now, the authors formally prove that the certificate issuance process can withstand the compromise of N CAs or trusted parties. This process can thus be used to establish a true public key for a domain in a way that is difficult for an adversary to forge. However, the drastic change to the certificate issuance process imposes a major adoption burden on domains and CAs. Moreover, a misconfiguration can establish the wrong key as a domain's true public key, leading to that domain becoming temporarily inaccessible for clients who are using ARP-key. And finally, the security level N is set system-wide, meaning that in the case of any change, there needs to be a flag day in which clients begin using this new level. Now, these two works highlight the main problem that we are addressing. We have not had a system that is both smoothly deployable and can prevent man-in-the-middle attacks. And when we consider this problem, we identify three major desired properties. First, we want to allow domains to establish what we call authoritative public keys in order to prevent man-in-the-middle attacks. At the same time, we want to make sure that even if a domain is misconfigured, it can easily recover even without a long period of availability. Finally, while we are incrementally deploying these improvements, we want to ensure that an adversary cannot carry out a downgrade attack, tricking a client into using the existing weaker PKI or no PKI at all for a domain that has an authoritative public key. So to address this problem, we propose certificates with automated policies and signaling, or CAPS. CAPS uses CT and other global public logging systems as a way for domains and CAs to communicate information. It uses this information to build a data structure that can signal both the deployment of HTTPS and of CAPS to clients. With a global view of the Web PKI, CAPS allows domains to establish authoritative public keys while keeping certificate issuance as is. And we can use these authoritative public keys as a foundation to deploy further improvements to the Web PKI, such as ARP-key. So let's dive into the design of CAPS. In CAPS, we extend the standard Web PKI architecture, so a CA issues a public key certificate to a domain and publicly logs that certificate, and the domain and client can carry out the standard TLS handshake. Now we add new entities called log aggregators, which collect certificates from public logs, as well as scans from certificate databases such as Census for completeness. They then build signaling sets, which are data structures that compactly represent which domains can be accessed over HTTPS and over CAPS, and these signaling sets are sent to client browsers. Log aggregators also create policy proofs, which are signed messages that indicate a number of certificates that a client should expect for a domain. Domains fetch these policy proofs from log aggregators as needed and provide them to clients during the TLS handshake. Now let's take a look at the details of how the signaling set is structured. Remember that a log aggregator uses scans and certificates to get a global view of the Web PKI. It can thus determine which domains have a certificate at all and which domains have deployed CAPS, which we interpret as having multiple independent certificate chains for the same public key. We'll discuss this concept more on the next slide. A log aggregator takes this set of domain names and builds a deterministic acyclic finite state automaton, or DAFSA. This data structure supports set membership queries, and we can use techniques in the literature to both build this data structure in a single pass and to encode it as a compact bit vector. Now, to further optimize the size of the DAFSA, we created a technique called path compaction, which looks for sets of connected nodes that can be combined to minimize the size of the final encoding. For example, sequences of nodes with one edge in and out can be combined into single edges, as you see here. So for example, A.F. And in large DAFSAs, compacting nodes with one edge in or two edges out, or vice versa, also yielded significant space savings. We can actually estimate the effects of compacting any given set of nodes by considering the change in information entropy in the set of edge labels and in the set of destination nodes, which are the nodes within edges. But for sufficiently large DAFSAs, it was far faster to just automatically compact the types of sets that we described earlier. All of this enabled us to store a succinct, searchable representation of the set of all domains that deploy HTTPS and/or CAPS. So now let's take a look at how CAPS creates policies for domains' authoritative public keys. Now, a given public key of a domain can have multiple chains of certificates that certify it. Here, each hex string represents a public key fingerprint, and the arrows denote certificate issuance. Now, we can see from this graph that if this public key were that of an attacker, at least 2 CA private keys would need to have been compromised. Now, for this public key, a log aggregator would build a graph like this for all public keys associated with a domain name and calculate this value using min_cut that in some ways represents the confidence that we have in this key's authenticity. Now, for a given domain name, a log aggregator then creates a CAPS policy, which is simply the maximal number of CA keys that it would need to be compromised to forge this public key. Now, rather than simply establishing this specific key as authoritative for a domain, we say that any key backed by this number of independent certificate chains can be treated as authoritative. This has several advantages. First, each domain can choose its own security level and set its policy value accordingly. Second, we assume that a domain can always obtain more independent certificate chains for itself. So in the case of a misissued certificate or an attempted man-in-the-middle attack, the domain simply obtains more certs. Third, the domain can simply obtain certs as it does today because logs and scans ensure that this information gets to the log aggregator, so the domain doesn't need to do any extra work beyond obtaining certificates to raise its policy value or to establish a new authoritative key. With all that in mind, let's take a look at how a client and server actually establish a connection. So a user Alice begins by first checking the signaling set for the domain that she wants to access. And based on the response that she gets in the signaling set, she knows how to initiate the TLS handshake with Bob. Suppose that Bob has deployed CAPS by having multiple independent certificate chains for the same key. Then Alice's hello message contains a TLS extension, which specifically requests a number of policy proofs for Bob to send over. Bob is going to send that his certificate, the requested number of policy proofs, and the other independent certificate chains that he has. Now remember that a policy proof is a signed message from a log aggregator containing Bob's policy value, which indicates how many certificate chains that Alice should expect. Alice can request multiple policy proofs to make sure that a single misbehaving or delayed log aggregator doesn't result in her getting an incorrect policy value. In practice, we expect that this value K won't exceed 2 or 3. Alice can then verify these certificate chains, and if all goes well, establish an encrypted communication channel with Bob. Let's now explore how CAPS performs in practice. So I've mentioned that the signaling set can succinctly represent all domains that deploy HTTPS and/or CAPS, but you may be wondering what I mean by succinct. So to test the overhead of the signaling set in practice, we collected about 3 years of certificates and filtered out those that were expired, not recognized by major browsers, or had DNS names that were no longer active. And we ended up with a set of about 64 million names as of July 3rd, 2018. These names in plain text took up about 1.5 gigabytes. Using the compression utility ZPack with parameters chosen for the best compression ratio, we were able to compress this set into an archive of about 104 megabytes, which for us represented a best case scenario, but still needs to be decompressed and loaded into memory for efficient searching. We found that using our DAFSA-based approach, we could build a signaling set that was about 190 megabytes, and we could use ZPack to compress that down to 148 megabytes when transmitting that to clients. So remember, this is for every domain observed on the web, and we can further optimize this by considering a smaller set of the most popular domain names. But it's important to note that with our DAFSA-based approach, this 190 megabytes is also the representation in memory, which allows us to query this in a much more memory efficient manner. Now, updates to this set, as you'll see on the right, were only about 3 megabytes per week when encoded as a DAFSA and compressed. This equates to about 439 kilobytes per day, which is just about the size of the Google homepage. We're fairly confident that as the costs of storage and memory fall, this overhead will become even more modest for clients. We also tested the connection establishment latency to see the overhead of querying the signaling set and transmitting and verifying extra information, such as policy proofs and additional certificate chains. We implemented CAPS with an Nginx server and curl client to isolate the overhead that CAPS would impose, and we tested the TLS handshake both over the loopback interface and over a wide area network. And in both cases, we found that the average increase in latency was about 5%, or on the order of milliseconds. But we'll note that with the variance in latencies that we observed, the average latency with CAPS is not actually statistically significantly more than that of the existing TLS handshake. So CAPS really imposes only a modest overhead in practice, both in the signaling set and in connection establishment. So I want to conclude by looking back at what CAPS has allowed us to achieve. We can use a global view of the Web PKI to signal deployment and thus prevent downgrade attacks for every domain in the web. We can use this global view to build flexible policies that prevent man-in-the-middle attacks while avoiding the many pitfalls of misconfiguration and avoiding inaccessibility. We've shown that CAPS imposes only a modest overhead on storage, memory, and on TLS handshake latency. And with all of this, we see that CAPS leverages existing technology to provide for a more secure and smooth transition to a more resilient Web PKI. Thank you.